identify functional groups and parts of molecules that give them unique properties and predictable properties. We're going to be learning more throughout the A, B, and C series about the properties of all different functional groups. Well, today I'd like to continue our discussion of the conformations of cyclohexane. We're going to focus on the main stable conformation, the chair conformation, and we're also going to talk a little bit about other conformations, both in half chair and twist boat conformation, as we go through and get to understand this molecule. And I'm delighted to see everyone has cyclohexanes. I see a boat. That's a beautiful boat in the fourth row. So if you have a boat like this, you can pull up one end to make a chair. The chair stands like a three-legged stool with three axial hydrogens pointing down. It sits very nicely on your palm of your hand. If you have a big hand, you have three axial hydrogens pointing up. Last time, when we started talking about cyclohexane, we learned how to draw it. We saw the projection of it. We learned where the axial and equatorial hydrogen atoms were. So I just want to talk a little bit about a ring flip and what happens. I'm only going to focus on the hydrogens attached to one carbon right now. So let's imagine we have HA and HB. And in my model of cyclohexane that I'm now projecting up off of my camera here, you'll see I put the red ball just representing any old atom in an axial position. We can think of it as a hydrogen atom here. We talked about the process of ring flip. This ring flip occurs millions of times per second. And in plain old unsubstituted cyclohexane, you generate a second equivalent chair conformation when it undergoes ring flip. What's important about this is that the hydrogen that was equatorial, in fact, all 6 of the hydrogens that were equatorial, now become axial. And the hydrogen that was axial becomes equatorial. So I'm going to do this with my model on the camera, and I urge you to follow along with me, because this really is the way you learn this. It's by touching these models, manipulating them, and visualizing them. So I've put a red ball to label one of the axial hydrogens, and a white ball to label one of the equatorial hydrogens, and I'm just going to grasp that carbon atom and pull down and rotate, and at the same time I'm going to pull up on the other side, and then I'll just touch up the conformation and make sure now my white atom and the other 2 hydrogens, we'll call these the 1, 3, and 5 positions, that they're standing up. 1, 3, 5, and then we have the others pointing up, and you'll notice our red ball now has gone from the axial position to the equatorial position. So the key on this is to be able to sort of grab both sides. It's a very simple movement. You just go down on one side, up on the other, and you just sort of wiggle it, and then you make sure that you have 3 hydrogens pointing up and 3 hydrogens pointing down, and then you have a perfect chair conformation. So the trick is it's alternate hydrogens. So if your molecule looks like this, if you have 4 pointing down, if 2 in a row point down, you have a boat or a variant of a boat conformation. Now let me show you what we go through in doing this. I'm going to sketch this out and show you the various conformations and how this process occurs. So let's imagine we start to pull down on this side here. So I've left the left side alone, and I've started to pull down on the right side. And halfway through, we come to a point where 5 atoms are coplanar. I'll hold it up over here, and I'm going to put it up on the camera, although it's a little bit hard to see. You notice how at this point we have 5 atoms, 1, 2, 3, 4, 5 carbon atoms are coplanar. We call this a half chair. A half chair is a high energy point, what we call a transition state. Remember, as we move over an energy surface, just like we've rotated about the bonds of ethane or about the bonds of butane, you go through a series of peaks and valleys. The peaks we call transition states. They're high energy, unstable forms. The valleys we call conformers in the case of molecular conformation. And so we're moving over a high energy peak, a half chair. And we continue along. There's actually a few little bumps in the road. I'm going to give you the simple version, and then I'll show you something a little bit more complicated. When we come along and continue to move down, we get to a boat. It's called a boat because it looks like a rowboat. It looks like a rowboat that sits on top of the water. The boat conformer has a lot of eclipsing. We have hydrogens banging into each other across. Still unstable. Actually, if you want to form something stable, you just give it a little bit of a twist. That eliminates some of the eclipsing interactions. It's called a twist boat. That's actually a stable but high energy conformer. The half chair is about 10 kilocalories per mole in energy above the chair conformer. The boat is about 7 kilocalories per mole higher in energy. The twist boat is about 5 kilocalories per mole higher in energy. All right, so you're at a boat and you're sort of halfway there, because now what we've done is to pull down, and I'll go up to our display here. I'm going to go back to a boat. We pull down the entire right-hand side of the molecule as it's appearing on the projector. It's my left-hand side, but you're right. Now we start on the left-hand side, and we flatten out once again. We're going through a symmetrical process here. And at that point where you're flat, where 5 atoms are coplanar, you're at another half chair. And now all we continue to do is to pull up on the right-hand side of the, as it's drawn there, the left-hand side. It's always reversed for me, the left-hand side of the molecule. And that's the whole ring flip process. We complete our ring flip by pulling up. If you want to do it quickly, you just do it at the same time. But if we want to sort of see it step by step, then you pull on one side and you pull on the other side. Questions or thoughts? It takes a little bit of practice and a little bit. Okay, very good. What do you have there? You have a boat standing just about on 4 legs. In fact, it's just sort of a twist boat. You notice the guys at 1 and 4 are hitting into each other. And what do you have there? Boat. And make it into a chair. Good for you. I'll show you a few other models up here. So I have here a chair, and I'll put up, let's see, what do I have here? I built these the other day. I can put up, here's our half chair. There's our half chair, and you notice how we have 5 carbon atoms coplanar with each other. So that's halfway through the process of conformational interconversion. Here's our twist boat conformation. That's a twist boat. So yeah, this is a boat. And the really bad thing about a boat is you have eclipsing interactions. Remember those eclipsing interactions in ethane that were really bad where the H's line up? So you've got hydrogens banging into each other at the 1 and 4 positions across the top of the boat. And you have this eclipsing interactions. If you just distort it a little bit, just twist it a little bit, now you have your twist boat. Yes? Upside down or right side up doesn't matter. You have a boat there. Just grab the 1 and 4 positions. Give it a little twist. Yep, not even so much. Back off. There you go. Perfect twist. All right. Well, our TAs are going to be taking us through some exercises this week with molecular models on cyclohexane. And we're going to get more experience on this in the discussion sections, but I'm absolutely delighted to see you playing with the molecular models, because this is how you start to learn and get familiar. Another question? Beautiful question. How come the half chair has more energy? How come the half chair is more energetic? Okay, the half chair is bad because, look at that. You see all those eclipsing interactions? Let me stop this from rocking. All right, so you notice as we Newman project, you see an eclipsing interaction right here where my cursor is? And another eclipsing interaction. And another eclipsing interaction. Every hydrogen-hydrogen eclipsing interaction overlapping the filled orbital created by the sp3 on the carbon bonding to the hydrogen, overlapping with another one on an adjacent carbon, costs 1 kilocalorie per mole. And we have 10 of those interactions in the half-chair conformer. So there's roughly, well, I guess it's 8, and there's some other bad interactions, but we have roughly 10 kilocalories per mole of strain associated with the high chair. So this ring flip between one chair and the other chair, which in this case are degenerate, which means they're the same, occurs a million times, millions of times per second. Molecules have lots of energy in them. They're constantly vibrating and rotating. And this occurs millions of times per second. And there's enough energy to go over that energy barrier, over the hump of the half chair and the boat and the other half chair, all the way to the other chair, millions of times per second. Those are energy barriers. Those are the peaks. The two degenerate chairs here are equal in energy. What I'm going to do now is to put a substituent onto our molecule and so we're going to make the two different chairs not the same, and we're going to make them unequal in energy. So let's go now to methylcyclohexane. And I'll write out a skeletal structure. You can write it like that. If you want to be explicit about having a methyl group on there, you can write it like this. And what we're going to do is we're going to put the methyl group, for starters, in the equatorial position. We call this the equatorial conformer of methylcyclohexane. If you have a methyl group in your bag, in your book bag, or whatever you brought for today, just go ahead, get back to your chair cyclohexane, put that methyl group in the equatorial position. Get back to the three-legged stool, back to 3 hydrogens pointing down, 3 hydrogens pointing up. Good, just like you have over there. Just like you have over there. Grab a methyl group, put it in the equatorial position. And I'll pop up a equatorial methylcyclohexane just to give you a little bit of guidance here. All right, so I have an equatorial conformer of methylcyclohexane spinning around up there. Do you like these models? If you want to play with them on your own computer, the software that I got actually gives me a license to share it with students. It's not easy software to use. I use it in my own research. It's pretty easy for viewing. But if people want it, I can email a link afterwards. People want it? All right. I can't really provide a lot of tech support on it because it's really complicated to use. The easy part is viewing. I have some web pages set up with a lot of these structures. I've just set it up as a helper application for Firefox, which means every .pdb file opens automatically in it, so if you do that, you get the same performance I get. Anyway, it's fun software. You actually can even build models like this if you know what you're doing in there. And maybe what this can do, I think you still definitely want to be using the molecular models. We're going to have questions on them on the exam and discussion. But if this can complement your use of molecular models, and you like computers, if you don't like computers or find it hard, just forget about it, because it's, it is tricky software, but it's also fun and powerful. All right, let me get the lights off of the screen here so I can go back to what I'm doing. All right, so now we're going to do a ring flip. Just as we did before. And remember, in the ring flip, you pull down on the side on one side and push up on the other side. Like so. And now, you got it, your methyl group is pointing upwards. Rotate you're beautiful. Now rotate your methyl group. Beautiful molecule. Now rotate your methyl group So your CH bonds are not staggered. Everything else are not eclipsed. Everything else is fantastic. Just rotate about. Beautiful. Okay. I'm going to do the same thing over here. All right. And what I'm going to do is to draw out the methyl group. Actually, for starters, I'll just write it as CH3, and then I'm going to redraw it. All right, so here we are. Now, our methyl group has gone to the axial position, and the hydrogen has gone to the equatorial position. And looking around, I see a lot of correct ones, and I'm really happy on this, because this means you're starting to get it. You have a boat, or a twist boat here. All right, let me do this with the molecular models, and then I want to talk about the energies of this. And let's see, I've done it the other way on there, so I'm just going to rotate. What I'm typing now just makes the picture a little nicer. And a lot of this is menu driven as well. Okay. All right, so let's talk about this. This is the axial conformer. And what's bad about, let me turn off the lights here on the blackboard. All right. What is bad about the axial methyl conformer, I think you can start to see. This methyl group is hitting into these hydrogen atoms. Let me draw this out explicitly. Whoops. So I'll draw on my hydrogens. Draw on this hydrogen here. Now the last thing I just want to do is to draw on the hydrogens on the methyl group. One's coming out, one's going back. And can you see how these hydrogens are hitting into each other? It's what we called steric hindrance when we talked about gauche butane. And in fact, there are two gauche butane type interactions. In other words, embedded in the molecule is one gauche butane on the front here and one gauche butane on the back. There are two bad hydrogen interactions where you have the methyl group's hydrogen hitting into those bottom two hydrogens. Those interactions each cost 0.9 kilocalories. Each. And so we have two of those in this case. So the the axial conformer is 1.8 kilocalories per mole in energy, higher than equatorial. You can really see it if you imagine your hydrogens taking up space. The hydrogens are, of course, not just little dots at the end of the rod. The hydrogens have a radius of 1.1 angstroms. and that means they're big enough to bang into each other. Here I can show you. I'll just make this into spheres. If you want to do it, if I'm going to show you on the software, if you want to do it, you notice where my cursor is? That show means convert the atoms to. If I go show spheres, we get spheres. If I go hide spheres, you notice where I'm pulling H is hide, we get rid of them. So I'm just going to go back to show spheres. And now I'm just going to zoom in and rotate this guy. Let me stop rocking here for a moment. So we're looking at the bottom of, let me click rock to turn it off. We're looking at the bottom of the molecule. And you see those hydrogens right where my cursor is hitting into each other. That's these bad steric interactions. These hydrogens are spheres. They're banging into each other. The hydrogen on the axial methyl group is banging inward. We call these interactions 1,3 diaxial interactions. Now, as you proceed in the course, you're going to learn more about energy. I've been mentioning some numbers already, and I want to, you'll get more of a feeling later on, but I'm going to remind you of the things I've said. The energy barrier for rotating about ethane is 3 kilocalories per mole. That's a very low energy barrier. At room temperature, we cross it more than 10 billion times per second. The energy barrier for flipping cyclohexane is 10 kilocalories per mole. At room temperature, we cross that energy barrier about 1 million times per second, a little more than 1 million times per second. That's a statement of rates. You're going to learn more about this. We're going to start to talk about reaction coordinate diagrams. But what I want to talk about now is difference in heights of the valleys. And we already saw this with butane. We saw that with butane, the gauche conformer of butane was 0.9 kilocalories per mole, higher in energy than the anti-conformer. Both the anti-conformer and the gauche conformer lie in a valley. That's the definition of a conformer. It's a stable conformation. But the gauche conformer is 0.9 kilocalories per mole, less stable. Here we have 1.8 kilocalories per mole of energy difference. What that means is at room temperature, at 298 Kelvin, if you have methylcyclohexane, 95% is in the anti-conformer. Say 95% methylcyclohexane. Meaning the methylcyclohexane molecule. And 5% is in the gauche conformer. The my brain is not connected. Yes, equatorial. Thank you. Yes, 95% is in the equatorial conformer. 5% is in the axial conformer. My mouth was still on butane, and my brain was somewhere else. So anyway, all right. I want to talk about making things really bad now. So let's go back to our axial conformer. So let me do one last thing. I'll embellish this drawing to show a big back arrow here to show that we are going back on our equilibrium. And now what I'd like to do is to talk about what happens if we go to a tert-butyl group on cyclohexane. So, same drawings that I made before. But now what I'm going to do is a ring flip that puts the tert-butyl group in the axial position. What do you think the implications are for the energy of the axial Tert-Butylcyclohexane conformer? No, this is great. Don't be sorry. What do you think the energy implications are for your axial Tert-Butylcyclohexane conformer? Pretty bad, yeah, really bad 1,3 diaxial interactions. Really bad 1,3 diaxial interactions. That tert-butyl group just doesn't want to be axial. I'll make the longest back equilibrium arrow that I can possibly make. Tert-butyl just manages to lock the methyl group, the molecule into the equatorial conformer. All right, let's explore one last situation here. All right, let us explore this molecule. On the same face of the ring, we have a tert-butyl group and a methyl group. We call this the cis isomer. Specifically, cis-1 tert-butyl for methyl cyclohexane. And now we have two choices. So this is our first exposure to stereoisomerism. This is the cis stereoisomer. The trans stereoisomer is the molecule in which they're opposite on the ring. So this is the trans here. And the cis puts us in an interesting position. Because now we have a choice. We can either have our tert-butyl group equatorial and we can either have our tert-butyl group equatorial and our methyl axial, or, and I guess I'll draw it right over here, we can ring flip to have our tert-butyl group equatorial axial and our methyl group equatorial. Two different conformers. Now I just said something about the tert-butyl group. This molecule has to make a choice. Does it want to be in the conformer on the left, or does it want to be in the conformer on the right? On the left. So you've got a choice. Damned if you do, really damned if you don't. And as a result, the molecule adopts this conformation. This is the stable conformer. I'll call it more stable conformer, but in reality, it's close to 1,000 to 1 times more stable. So the molecule very strongly prefers this conformation. All right, well, this is where we will stop. Next time, we will start picking